to introduce Arpan Gujarati and Jonathan Mace, who are our guests for today's SysRead talk, which is about a upcoming OSDI paper, whose very nice title is Serving DNNs Like Clockwork, Performance Predictability from the Bottom Up for Machine Learning. So without further ado, I will hand it over to Arpan, and we are ready to go. Arpan, if you can just clarify if you're happy with questions throughout, or if you would prefer us to keep them to the end, I think that would be helpful.
Yeah, so I think I'm perfectly fine with questions in between. I mean, whenever you have a problem, just stop, but like, don't wait for me to see the raise hand or anything, just like interrupt me.
Excellent. All right, over to you.
Okay. Okay, so first of all, thank you very much for inviting Jonathan and myself here for your systems reading group. In this talk, I'm going to present our design of the system Clockwork, which is a platform for serving deep neural networks. It's a platform designed to serve thousands of models concurrently. This work is going to appear at OSDI next month, and it's a joint collaboration between researchers from the Max Planck Institute for Software Systems and from Emory University. So let me start by explaining Clockwork in a nutshell. So the focus of this work is machine learning inference. Machine learning inference today is part of many critical, it's part of the critical path for many user-facing requests. There are plenty of examples, including picture identification on social media platforms, music recognition on mobile phones, and even health monitoring on smartwatches. And we are particularly interested in machine learning inference using deep neural networks, because computation CO is difficult to manage in the cloud. Now, the starting point of Clockwork is a very simple observation. Across a vast majority of deep neural networks, if you execute an inference, the execution time is actually very predictable. Clockwork therefore builds an end-to-end predictable platform using this observation that can serve deep neural networks in the cloud. And in general, Clockwork is able to support thousands of models concurrently per GPU. It's able to mitigate tail latency significantly while supporting tight latency SLOs of tens of milliseconds. And it can do all of this with varied workload conditions as well. So in this talk, I'm going to explain you the design of Clockwork, in particular, how Clockwork is able to preserve and exploit the DNN execution time predictability. Let me first start with a quick background on inference serving platforms. Now, inference serving at the cloud scale or in the data center is a difficult problem. Service providers typically have to deal with thousands of trained models. And as you can see in this figure, these models can have different resource requirements, different memory requirements, and also different execution time. Also, the request for these models may arrive at different rates and regularity. They can be periodic in nature, they can be bursty, or they might have a sustained rate, high rate, and they can also be arbitrary in nature. Also, in addition to satisfying these different kinds of workloads and different kinds of resource requirements, there are also service level objectives that the service providers must comply with. For instance, every request must finish its execution within a certain deadline, for example, 100 millisecond SLO. Now, to satisfy these kinds of requirements, it is inevitable that the cloud providers use some form of hardware accelerators like GPUs. And the reason is that CPUs often aren't fast enough to execute or satisfy these kinds of latency requirements. The trade-off, however, is that GPUs are also much more expensive than CPUs. And for many models and users, their workload is just not high enough to justify the use of a dedicated hardware accelerator. The goal, therefore, is to maximize sharing in the cloud, but while meeting the individual latency SLOs of each model and user as well. Now, unfortunately, existing systems are not able to satisfy the latency SLO requirement very well. And more specifically, they incur very high tail latencies when they are trying to serve such varied workloads. Let's explain this with a very concrete example. In this experiment, we do some evaluations on the Clipper model serving platform. In this experiment, we deploy 15 trained ResNet 50 model on a single GPU worker. We configure Clipper to satisfy a 100 millisecond SLO. And we then configure the client to send up to 16 concurrent requests per model to the Clipper. And we then measure the inference latency that we observe on the platform. In this graph, I'm plotting the CDF of the inference latencies, and the y-axis is configured such that the high percentile values are magnified. So let's see the results. What we can see here is that almost the entire tail latency is in excess of 100 millisecond. And in fact, the 99th percentile tail latency is twice that of the 100 millisecond SLO. Now, this phenomenon of having high tail latency is not specific to Clipper or even model serving platforms. It basically arises from the fact that different subcomponents inside a system can have unpredictable response times, which can accumulate and lead to unpredictable or high tail latencies. So for instance, Clipper tries to maximize the resource utilization using techniques like running the DNN inference in parallel over a GPU. Now, this does allow Clipper to achieve a higher throughput. For instance, running DNN inference concurrently can improve throughput by up to 25%. But as we show in this graph, it also leads to very high variance in the tail latency. Now, such a high variance in the tail latency is not a fundamental problem in the design. It's just a byproduct of the design choice. For instance, if you decide to run only one DNN inference at a time, then the latency is actually quite predictable. And this is the starting point of Clockwork. Clockwork adopts a contrasting approach when it comes to model serving in comparison to prior model serving platforms. It decides to preserve the DNN predictability at every stage of model serving, and therefore it does not incur high tail latency by design. So let me show you the results where we repeat the Clipper experiment, but with Clockwork. In this case, both the 99th percentile tail latency and also the higher latencies are actually well within the 100 millisecond SLO. And Clockwork is able to manage such fine latencies without sacrificing the throughput, as I will show you in the evaluation later in the presentation. All right, so how does Clockwork achieve such predictability? How does Clockwork translate the DNN predictability into end-to-end predictability? Let me explain this by first explaining the three main design principles underlying Clockwork. Recall that our goal is to not just serve one model, but thousands of models across many different users and with limited resources. Therefore, sharing is inevitable. In fact, we want to maximize the sharing because GPUs are also expensive. The problem with sharing is that it can lead to contention, there can be unbounded delays, and this means that even if one inference request is predictable, the response time of DNN inference on a worker machine can be very unpredictable. So as a first step, we want to make every Clockwork worker as predictable as possible with respect to the external environment at least. And we do this by stripping off the worker of all decisions that it can make. So for instance, Clockwork workers do not make any scheduling decisions, they do not make any state management decisions, and so on. They simply execute all actions which they are told to execute, and the actions are sent to them using a remote set of APIs. Now, instead of letting the workers decide what they should execute and when, we consolidate all decisions at a central controller instead. This way, the central controller can manage an accurate representation of the global state, which in turn can help it to make more smarter decisions or more proactive scheduling decisions and so on. So in short, the central controller makes all the decisions and it sends the actions to all the workers which simply follow these actions. The last principle is that Clockwork scheduler is aware of the deadlines and the SLOs. It tries to maximize the resource utilization on the workers, but at the same time, because it is aware of deadlines, it will not schedule any work on a worker such that the work does not finish on time. So for instance, if a request arrives and Clockwork says no request, it will simply cancel the request so that the resources are not wasted. So this way, Clockwork is able to not just manage good tail latency and comply with SLOs, but also provision the workload with high throughput. So now let me go through each design principle one by one. I will start with explaining the first design principle, which is how can we design a predictable worker?
Arpan, can I ask a question?
Yes. Sorry, who is this?
Rodrigo.
Oh, hi.
Yeah, sorry for the noise earlier. So you're basically saying that, yeah, there's this, if you answer, you're not wasting resources on things you can't fulfill. So this essentially means that you're doing admission control, right? The graph that you showed before where you compare Clipper with Clockwork, is that serving the same number of requests?
You mean the Clipper graph and the Clockwork graph?
Yeah, so this means that you were offering some load that was you could fulfill, right? You're not dropping any requests here.
So in the case of Clipper, we are not doing any admission control on our side.
Sure, but in Clockwork, are you dropping any requests to achieve the Clockwork graph?
Clockwork is designed to drop request if it cannot satisfy the SLO. But I will present a detailed evaluation in the end where we show that we actually end up dropping very few requests, very negligible amount of requests.
Okay.
I can answer this question for you. I did this experiment. The answer is that this we get the same results for open loop workloads, closed loop workloads, workloads where the offered load is much higher than the system can serve, and workloads where the offered load is at or below the capacity of the system. It's very standard.
So wait, in the second to last one you mentioned, which is when you offer more load than the system can sustain. Yep. This isn't necessarily dropping requests, right?
So Clipper will drop Clipper will time out requests if it has too much offered load, as will Clockwork.
Clockwork will drop them, right?
Both Clockwork and Clipper. Yeah, Clopper, that's a good name. Yeah.
Okay, cool. Thanks.
Okay. Right. So
yeah, I have a question about the scheduling part. As I understand, I mean, the main issue with predictability would be VRAM trashing of models. Basically, when you have multiple models and you need to replace them in VRAM.
Could you repeat the question? I had some noise on my side. Michael, could you please repeat your question?
Yes. So here in the slide, you have the point 3 deadline aware scheduling for SLO compliance, and the big part of SLO compliance and predictability is about if you need to load the model from RAM to the video RAM. And I mean, I would expect the biggest part of unpredictability is trashing of models.
Yeah, so I would come to this in the next 1 or 2 slides, how we manage the memory for the models. So maybe you can defer the question if it's not answered until then. Okay. Right, so I was about to say how we come up with a predictable worker. So in general, you can think of a worker as comprising of a main memory, which is typically a few terabytes in size, and a GPU memory, which is typically a few gigabytes in size. Therefore, in fact, it's quite common for all the models to reside in the main memory, and only some models to reside in the GPU memory and use the GPU memory as a cache. So you can have models loaded into the GPU memory in and out based on demand. Now, let me explain how a typical inference request works on a worker machine first. Typically, users upload pre-trained models in advance. They reside in the main memory. And when an inference arrives, the model first needs to be loaded into the GPU memory. And this might take a few milliseconds depending on the size of the model and the size of the model weights. And we call such a request or such a model as a cold model because it does not exist in the GPU memory yet. But once the loading has happened, the inference can be executed on the GPU. Now, if another inference request for the same model arrives, because the model is already loaded, we can directly execute it on the GPU. And we term such models as warm models. In general, as I show in this figure, there could be multiple models loaded inside the GPU memory. And also frameworks can decide to execute multiple GPU inferences in parallel. Now, the goal of Clockwork is to make this entire process predictable. But what can be the main sources of unpredictability in this end-to-end execution of the inference request? I can point you to three main sources here. One is the queuing delays. For instance, the workers might decide to implement best effort queues, which might reorder request and therefore lead to unpredictable response times. The workers can also decide to run inferences concurrently, and this also leads to unpredictable response times because we do not know the scheduling policies used inside the GPUs. These are typically proprietary and also not documented that well. And finally, the memory management itself can be a problem because depending on whether the model is cold or not, the latency can vary by an order of magnitude. For example, in the case of ResNet 50, the time to simply execute an inference is 2.3 milliseconds, whereas the time to first load the model and then execute the inference is 10.6 milliseconds. Clockwork therefore tries to get rid of all these sources of unpredictability and build a more predictable Clockwork worker process. And in order to do so, we first have a simple heuristic or decision, which is Clockwork executes only one inference at a time. And this is not really a bad idea because, first of all, DNN inferences are themselves quite a parallel operation. So they do not waste a lot of GPU. And as I showed in one of the graphs, throughput gains are only up to 25% if you execute inferences in parallel. And even this gain of 25% quickly goes away if you start batching multiple inputs when executing a single inference. So basically, Clockwork decides not to execute inferences in parallel. Secondly, Clockwork decides to manage the entire GPU memory on its own, which means that the workers pre-allocate the entire GPU memory in advance, and they expose load and unload action APIs, which allow loading in and loading out of models from the outside. And finally, Clockwork does not implement any best effort queuing logic inside the worker. There are only two queues inside a Clockwork worker process. One queue manages the load and unload actions, and another queue manages the infer actions. And these are both deadline-driven queues. And they execute actions one at a time. So at any point of time, there can be at most one load or unload action, or there can be at most one infer action. And if there are dependencies between load and infer, for instance, if there is an inference request for a model which is not loaded, it is simply canceled by the worker.
When you say execute inference one at a time, it's one model at a time or one?
One inference at a time. It's not per model, it's across all models. There's one inference happening at a time.
I would expect backing multiple requests.
Right. So
I think it's one action at a time.
Right.
So an infer action can specifically specify this is an infer action that batches 5 inputs.
Yeah.
Right. So for a single model, of course, the input could be an inference request, but that request is actually a batch request for multiple inputs from the user. Does that answer your question, Michael?
Yeah, thanks.
Okay.
So just before we move on, there are two questions in the chat from Gulam and Linen. If your questions are still current, Gulam, do you want to go first? And you can pass if it's been answered already.
I think it's answered, but I just wanted to confirm that predictive a request serving latency prediction doesn't have anything to do with how the workload is like, right? You were mentioning like the workload could be like bursty, a constant like high or like unpredictable. It doesn't have anything to do with that, right? Because you have like one admission control possibly happening.
Yeah, so
okay.
So So the action latency does not have anything to do with the workload, but
Okay,
the
perfect.
end-to-end response times may be affected by the workload. Yeah.
Okay, perfect. Thank you. That answers my question.
Is there one more question from Lennon?
Yes. So my question is, what are configurable parameters so in the system can impact the overall tail latency? For example, if you increase the batch size, it definitely increase the number of the computations to take. So you can expect it takes a little bit longer. But having larger batch size will allow you to process more requests. So I believe there should be a lot of such factors in the system. Can you please highlight a few parameters here?
Yeah, so you are right in identifying that batch size can impact latency. Clockwork allows users to configure the maximum batch size, but we do not hardcode batch size in our scheduling. The batch size, we try to choose the best possible batch size at any point of time, subject to the deadline constraints. So yeah, maximum possible batch size is one configuration parameters. There are a couple of more parameters in the sense that how much workload do you want to schedule in advance, or how long do you want to wait until scheduling all the workload. So typically Clockwork's controller tries to minimize the amount of work sent to a worker. It tries to delay scheduling decisions as late as possible so that the decisions are as close to ideal as possible. So yeah, I guess these are the two main configuration parameters. I will describe the Clockwork controller with a couple of examples in the next few slides. So maybe if you have more questions on this particular topic, we can come back and discuss.
Sure, thank you.
Okay, great. Right, so basically we can summarize this part by basically saying that the Clockwork's worker does not make any decisions as such. Instead, it outsources all decisions via its action APIs, including the load and unload API and the info API. And these decisions are actually taken by a centralized controller. So the centralized controller takes in all the user requests and decides when, where, and at what time a certain load, unload, or info should happen. Now, obviously, in order to do this, the controller needs to know a lot about the worker states. So we have the workers regularly taking measurements of the actions that are executing on the respective workers, and they convey the measurements back to the centralized controller. And this allows the controller to have a good estimation of the latency profiles, understanding or figuring out which tasks are remaining or which actions are remaining on different workers and when a certain worker is expected to be free, and also know in advance which models are currently loaded in the GPU memory of which workers. And in turn, this can then help make better load balancing decisions. So one of the points which I just mentioned is this can help Clockwork controller kind of tolerate hotspots by delaying scheduling decisions as late as possible. So let me explain this scheduling part with a simple example. In this example, we are going to focus on only one GPU worker node W1. And suppose that the GPU memory of W1 has three models loaded, a red star, a yellow triangle, a blue circle, and that it is currently executing one inference action for the yellow triangle model. And as I show in the info queue, there are two more actions queued up. So they are expected to execute next as well. Now, this was basically scheduled by the controller a while back. So the controller precisely knows that worker W1 needs to execute 3 info actions for the yellow triangle model, and that it will get free at a certain point of time, which I denote here using time t free. So suppose that a new inference request arrives at this time now, at t now. Let's say a request arrives for the blue circle model, and the request has a very tight SLO in the sense that its deadline is actually earlier than the time at which the worker W1 is expected to be free. Now, in these kinds of scenarios, the controller simply cancels the request because it knows that the request won't finish on time. So there's no point executing it anyway. On the other hand, suppose that another inference request comes for the red star model, but its SLO is more relaxed, which means that its deadline is much further away. Now, Clockwork also knows that from its latency profile, the red star info action can execute and finish before its deadline. In other words, Clockwork's controller can verify that the sum of T free and delta info is less than T deadline, and therefore it schedules the info action on worker W1. So you might be wondering that until now I have been talking as of everything is exactly predictable on the worker side, and Clockwork's controller knows all this information exactly. But this is not always true because perfect predictability is impossible. So it's possible that there are occasional misprediction as well. For instance, it's possible that the last yellow triangle info action actually overshoots its expected execution time, which means that the red star info action cannot start on time as scheduled by the centralized controller. Now, to tolerate these kinds of mispredictions, Clockwork's controller also keeps track of the latest time at which an action should start. And therefore, the worker will simply cancel this particular info action if it fails to start before the latest timestamp. This basically helps to localize the impact of such mispredictions and prevent further cascading of faults. So in summary, such a centralized approach and SLO-aware scheduling not only helps prevent wasteful work on the workers, but it also helps manage dependencies like load to infer dependencies and to help choose a good batching strategy at any point of time. So that was the end of the design description of Clockwork. So I can take more questions on Clockwork's design right now.
I have a quick question, which is a clarification. So you said that the requests come in with an SLO associated, right?
Yeah.
And it sounded like different requests have different SLOs. Who configures these SLOs? Because in the motivation experiment you showed earlier, it seemed like the SLO was uniformly 100 milliseconds for everything.
So Clockwork is designed to satisfy request-specific SLOs, which means that each request can have its own independent SLO. In the earlier experiment, we had like a blanket configuration where all requests had 100 millisecond SLO, just like a ballpark figure. But in general, you would expect different requests to belong to different types of users. There could be like latency-sensitive clients, which may have tight latency SLOs like 50 milliseconds or 100 milliseconds. There could be batch clients who do not really care about SLO, who just want to use the spare capacity. So they might have no SLO or a very relaxed SLO of 1 day or something like that.
So the client sets the SLO.
Yeah, the client sets the SLO, and we do have the provision to manage request-specific SLOs.
Okay, thank you.
Question here. So how do you decide the best batching strategy? From my understanding, you have a queue for users from the user request, and then the model pull a request from this queue and predict its potential latency. And then this model will direct to execution queue is that how you decide this batching strategy?
Yeah, so think of it as on the controller, there's one global request queue, which is say scheduled by the deadline, which is derived from the SLOs. And at any point of time, you can estimate the amount of work that needs to be completed. So there might be different strategies possible. One possibility might be executing the next 10 requests with a batch size of 1. Another strategy might be executing the next 4 requests with a batch size of 4, and the following 6 requests with a batch size of 4 and 2 as well. So we evaluate all these strategies that are going to cause a deadline miss, and out of the remaining strategies, you can choose the one which maximizes batching, because we know that batching is good for the overall performance of the system.
Okay, so what factors do you consider to maximize this batch size? Like, I'm still a bit lost. Like, how do you decide the best batching strategy?
As I just mentioned, if there are 5 different strategies feasible that do not lead to deadline misses, we choose the one where the batch size would be maximum.
Perhaps Lennon, are you asking, let me ask a question. So an important point here is that the batch size is not static. It's not a constant.
Sure.
So it can do a batch of 16, then a batch of 1 arbitrarily.
Sure.
So the factors that go into this choice are how many requests are present.
Mm-hmm.
So how many requests are there queued? You don't want a batch size larger than the number of requests queued.
Mm-hmm.
And then within that, you want to maximize the batch size because that slightly increases the overall throughput your system can get.
Mm-hmm.
But if you choose a batch size that's too large, the action will take too long to execute. So some of the requests within the batch size will miss their deadlines.
I see.
So it's the maximum batch size that can satisfy the most requests with none of them missing their deadlines.
Yeah, that makes sense. But how does this model place here? Because there's a prediction model here, right? So does the prediction model takes the input of this number of requests and the output batch size? Or what's the policy to decide the
so the prediction part comes into play here when asking how long will this batch take to execute? How long does a batch size of 1 take to execute? How long does a batch size of 10 take to execute? And that's not something that requires any complexity. We use a running 99th percentile average of running 99th percentile of the last n requests. I don't know what value of n it was, 10 or 100 or something.
Okay, just give you a little bit of background here because it's very related to one of the work and the Facebook system team. They are trying to search for the configuration of the batch size for all these recommender systems. From what I have heard, like batch size impact the tail latency a lot. So once they have, Facebook have a very large recommender system. That's where the most revenue comes from. So they have thousands of these machines, and they are trying to find maybe thousands of configurations for this batch size. I think that would be a very interesting extension, and perhaps you guys can discuss with, like, I think Carl, I think is leading that project. So I think she will be definitely interested in this work.
Okay, so it would be actually good if you can point us to that work later on, maybe.
Sure, I will. Yeah.
I have one last question. I'm sorry. So in case like we are sending out the red inference, right? So do we send out it to like multiple workers or just a single worker? Because like I can see the value of like sending it out to like multiple workers in case like anything bad happens on that worker. We can still be able to like serve that request given like there's some availability on some other worker.
So I think you are referring to the standard principle of power of 2 choice, or these power of.
Yeah.
So they can help. So these are actually, we consider these as what we refer to as best effort heuristics to tolerate unpredictable backend execution times by using power of 2 like strategies. And because we have predictable workers, we instead decide not to use any such best effort strategies, and instead just manage very explicit scheduling on each worker. So we do not have any such mechanism in place right now in Clockwork.
Sure. Okay, perfect. Thank you.
But then following up on that very quickly, if the red request does get canceled because you can't make the deadline, then the centralized controller has to reschedule it, right? Because it's now in no other queue at this point.
Or drop it.
So in this
right, but there's ultimately some client that
request got canceled because of the misprediction.
But there's some client that wants this request to be fulfilled, right? If you just drop it, does the client have to send it again? Like, is the client just in bad luck at that point?
So maybe I can answer this in 2 parts. First, this depends a lot on the client model of request. The client can decide to schedule requests such that if a request is canceled, it sends the request again. So We do assume that in a way, because if a request is canceled, we don't try to execute it again. We just think it's canceled. Yeah. And
so this is,
yeah, go ahead, Jonathan.
no, sorry, please continue, Arpan.
I was just saying that instead we try to just maximize the number of requests that we can service, because it might be that we want to service up to 99th percentile request and 1% gets cancelled, and we don't deal with rescheduling of those specific requests.
So this is something that we glossed over a little bit with the specification of the SLOs. So the way that an SLO is in production systems is specified is the latency, the 100 millisecond latency is usually specified as a percentile, not as a hard deadline. And then it's also subject to a specific workload. Sorry, the latency is not specified as a percentile. What am I saying? I'm saying that 99% of requests will finish within 100 milliseconds, for example. The other percent can just be dropped and then retried by the user.
I see. So that puts a limit on how many you can drop, because they count against your SLO percentile.
Yeah, exactly.
Thank you.
A small question here. So are you assuming the time to process this request deterministic?
Yes.
Yes.
Okay. Well, but what will happen if a machine is processing many, not just this task? For example, the machine is training a deep learning model and while it's doing the inference. So the inference times can be a distribution with a very long tail. What will happen to that case? So this looks like, or you can consider what will happen if a machine is processing 1,000 requests at the same time. So the final execution time will be something like distribution. Is that right?
So this goes back to our starting principle, which is that DNN execution times are predictable, and this is something we actually show. So it's not just an assumption, but it's something based on actual execution profiling. But having said that,
did you do that profiling without any interference of other applications? Are you running like different applications on the inference server while doing the inference? So what will happen? Yeah, what will happen if you don't have predictors?
If you remember, the method is anxious of one inference at a time.
Oh, so I think we are not running these on shared machines.
Yeah.
If you want any kind of sharing, like if you have other applications running in the same OS, other virtual machines, then you aren't gonna get much out of this, because the operating system or the hypervisor can context switch your application out. It can introduce arbitrary delays. So we are assuming that these are on exclusive machines. That's our starting point.
Okay.
Okay, so I'm going to switch to evaluation now. So we implemented Clockwork in C++. The entire system is roughly about 26,000 lines of code in C++. And here are all the questions that we answer in the paper. We compare Clockwork to some of the prior model serving systems, including Clipper and Inference as a Service, Inf as a Service. We evaluate how many models can a single worker machine serve using Clockwork. We also evaluate how low Clockwork can go in terms of the latency SLOs it can satisfy, or in other words, how tight SLOs can we satisfy. And then we also evaluate if Clockwork can isolate performance of latency sensitive clients, which are tight SLOs, and batch requests, which have very relaxed SLOs, or which are just looking to consume the spare capacity on the workers. So we answer these questions using synthetic workloads in controlled settings. But we also have lots of experiments which deal with workloads from production traces. So these are more realistic workloads with lots of models and different workload patterns. And using these production traces, we answer the three main questions, which is, are Clockwork workers predictable? Does consolidating choice actually help achieve end-to-end predictability for these realistic workloads? And finally, does Clockwork's centralized scheduling scale with the number of workers? So in this talk, I'm only going to focus on the last 3 questions, but I would refer you to the paper to look at other evaluation results as well. So let me start with the description of our experiment setup for these last 3 experiments. Our setup consists of 12 worker machines, 1 controller, and 1 client. Each worker has an NVIDIA Tesla V100 GPU with 32 GB GPU memory. And to model the realistic workload, we use Microsoft's Azure function traces, which they recently released as part of the Usenix ATC 2020 paper.
So Arpan, just to remind you, Rodrigo is here. This was his thing.
I know. But yeah, sure. I mean, since Rodrigo is here, they might all have read the paper. So. Anyway, so this workload consists of about 46,000 function traces traced over a 2-week period, and it has a mix of different kinds of workloads. And in this work, we map the 46,000 functions to about 4,000 model instances, because this is just the right amount of number to saturate our 768 GB RAM in all our worker machines. And our model collection actually includes different kinds of model architectures like ResNet, DenseNet, Inception, and so on. These are quite widely used today. Okay, so let me get on with the evaluation results now. First, we want to figure out whether the Clockwork workers are predictable. Recall from the design principles that this was our first design principle, and it's very important for the rest of the Clockwork to work correctly that the workers are predictable. And basically, if there are lots of over predictions happening on the worker side, then it would lead to idle resources. On the other hand, if Clockwork's controller underpredicts the action latency, then it can also lead to a lot of SLO violations, and we do not want both of these. So to evaluate the predictability of each worker in this experiment, we ran the Microsoft Azure function traces for about 6 hours. The offered load was about 10,000 requests per second, and we measured the overprediction and underprediction errors throughout this experiment. So this means that every time Clockwork's controller schedules an action on a worker, we measure the action latency as estimated by the controller before scheduling and the actual action latency on the worker after it's completed its action, and then we compute the difference, in which we report here as overprediction or underprediction error. I once again show the CDF in this graph while focusing on the higher percentile values. So an immediate conclusion which you can derive here is that Clockwork consistently overpredicts more than it underpredicts. And this goes back to the point that Jonathan mentioned earlier, that Clockwork maintains like a sliding window of measurements, and by design, it looks at the 99th percentile value from this measurement. So Clockwork is designed to err on the side of caution, therefore it overpredicts more than it underpredicts. But most importantly, the magnitude of errors are actually quite small. So typical action latencies, info action latencies vary from 1 millisecond to 20 milliseconds based on the model and based on the batch size, whereas the underprediction and overprediction errors are 55 and 144 microseconds for the 99th percentile values. So this indicates that errors in general significant errors are quite rare, and most often the errors are very small in magnitude. All right, so now that we have shown that the workers are predictable, we want to evaluate if the whole design of consolidating choice and making decisions based on these predictions actually helps schedule such a realistic workload like the Microsoft Azure workload, which has thousands of models and different workload patterns. So once again, we have a very similar experiment setup like the previous experiment. The offered load is about 10,000 requests per second. There was also periodic spikes in the workload, which pushed the cumulative request load to about 12,000 requests per second. And in this case, all requests had a latency SLO of 100 milliseconds. So in the first graph, I'm illustrating the offered load and the goodput, which is basically the SLO compliant throughput. And in the second graph, I'm illustrating the latency of all the completed requests, which means any request that might have timed out because of deadline violation is not captured in this graph right now. So overall, these two graphs suggest that the workload is quite successfully scheduled by Clockwork, and in general, Clockwork can manage such diverse workloads with different kinds of workload patterns, with thousands of models, and also Clockwork is able to trace the periodic spikes as well as the irregularities in the offered load as well. And more specifically, you can notice that the offered load and goodput are almost identical. And out of about 208 million requests which were scheduled across this experiment, only 58 failed due to mispredictions. And all others, which are illustrated in this latency graph, completed well within the SLO. Now, in order to have such good performance, many different factors are involved. One of the factors is the batching size, as we discussed in some of the earlier slides. So we also evaluate the average batch sizes that are used for all the actions throughout the experiments. Typically, the average batch size remains around 2, and this is because there are not often many requests for the same model queued up on the controller. But you can see correlations between the periodic spikes and the spikes in the batch size as well. And this basically indicates that Clockwork is able to go for higher batch sizes whenever there are more requests queued or more requests pending on the controller. And this in a way helps Clockwork to absorb these kinds of periodic spikes or even smaller irregular spikes in the workload. Another factor that's important when managing such workloads is how does Clockwork manage thousands of different models? Because we saw that we cannot fit all the models in the GPU memory, so we need to balance between cold and warm requests. So once again, we measure the number of cold and warm models throughout the experiment. And in the last graph, we also measure the number of requests that went to cold models. So these are basically cold start requests, incur higher latency because of the loading time. So there are two things to note here. First, there are many cold starts, and this is inevitable because we just cannot fit all the models within the small GPU memory. So we need to keep on swapping them in and out. But more importantly, the number of cold requests is only a very small fraction of all the requests, 1.3%, which indicates that Clockwork is actually doing a good job at making sure that the requests are routed to workers which have the right models loaded into the GPU memory as much as possible. So yeah, those were a lot of graphs. Any questions here?
I had an unrelated question.
Yeah.
But, so is there an assumption that like the incoming request is sufficiently small that even though how many models are loaded into the vGPU memory, the GPU memory, the request that needs to get inferred is going to take like such a small VRAM that it's not going to matter, right? Compared to like all the models that are loaded. So like basically what I mean is like, even though the request has to be on the vGPU to get inferred by a model that's loaded on the GPU, there's never going to be like any case where we have to like swap out a model just to like serve a request, right? Basically, there's always going to be space for requests on the vGPU memory.
No, not really, right? If that was true, then we wouldn't see so many cold models. Here you see that throughout the experiments, about 1/3 of the models are cold. So basically, there isn't space for all the models. And because of the fluctuations in the work, they're constantly being swapped in and out.
I'm asking like model getting swapped out because like a worker had to like serve a request rather than like switch out a model. The model is already on the vGPU, but a request is coming in. There's not enough space, VRAM, to like load out the request. Basically, that's what I'm saying.
Yeah. So typically,
what I'm saying is like, is that like such a minor case that you're not worrying too much about it?
Yes. So ideally, this would not happen because the controller would ensure that if it sends an info action, the load action is already there. So either the model is already loaded or it has sent a load action before it sends an info action. So I think the scenario point would happen in the case of mispredictions occasionally. But in that case, again, the action request would be canceled and the feedback would go to the controller, and for the next action, the controller will wait for the load to finish.
Okay.
Like there would never be an opportunistic scenario on the worker where a request arrives, action arrives for inference, the model is not loaded, and the worker is not going to decide that now I want to load this model because the model is not loaded. It's only going to follow the actions.
I was talking more about like the input that goes into the model. For example, an image that needs to go through like some resonant model, right? I'm talking about that image. That image needs to be loaded on the GPU RAM, right? As well.
Yes.
And there could be cases when there's not enough space to like load up an image, right? That's what I'm talking about.
No, this would not happen because the
May I jump in?
Yeah, I was just about to say that the inputs are fixed size, so we allocate the necessary IO cache beforehand.
Okay. I guess that's fair. Okay, perfect.
Jonathan, you wanted to add something?
Oh no, that's all I was going to say.
Okay.
So it wasn't clear to me that that Gulan was talking about inputs.
Yeah. Okay. So any more questions on these graphs?
I could add some comments.
Just as a time check, right? We have 5 minutes left. I don't know how much more material you have.
I have one more experiment, one more graph mainly, so it's fine. So I can actually go through unless Jonathan wants to add some more comment on these graphs.
No comment.
Okay. Yeah, so let's get on with this. And so right, Clockwork works, yay. But you might be thinking that there is obviously a bottleneck here because we have a centralized scheduler. So does it scale? How well it scales? What is the upper limit and so on? So in order to evaluate the scalability, we did some more experiments with the Azure workload once again. The method here was simple. We use emulated workers because we didn't have enough GPUs in our cluster to evaluate with the real work. But from a controller's point of view, this does not change anything. So the workload on a controller remains the same. So this should give a good estimation of the scalability. Now, how do we evaluate the scalability? We measure the peak good put as we vary the number of workers, and for each worker, we vary the offered load. For instance, here for 40 emulated workers, I'm gradually increasing the offered load. And at a certain point, we see the good put stops increasing, and that is the peak good put for this particular configuration. So for 40 workers, the peak good put is around 37,000 requests per second. And we repeated this experiment for up to 150 workers. Here are the results. We can see that the scalability is linear up to 110 workers, and up to then here, basically controller is not the bottleneck. The workers are the limitation. But after 110 workers, we hit the peak and the bottleneck shifts to the Clockwork centralized scheduling. So yeah, in general, there are ways to get past by these kinds of bottlenecks. We haven't yet designed the system for scalability. There are different techniques you can use like partitioning and all. We leave these to future work. But yeah, if there are no more questions on the scalability, the next slide is the summary slide. So we can discuss the scalability experiment first if there are questions.
I would suggest that you conclude, then we'll have 1 minute for questions about the general system. Okay. Right, so let me conclude quickly. Our key idea is that DNN executions have a predictable execution time, very low latency variability, and we use this we translate this into end-to-end predictability by ensuring predictability in every stage of model serving. And then we demonstrate through evaluation that our system outperforms state-of-the-art platforms in terms of the latency SLOs it serves, and also the number of models it can satisfy. Our source code is open source, and we also have artifacts evaluated, so you can try and welcome to contribute. Thank you. All right, thank you, Arpan. Sure. Any final questions on the whole talk before we wrap up?
I want to be in the end of the queue for questions.
All right, going once, going twice. Rodrigo.
Okay, I think this is really cool. I really like the principle of reducing or removing the unpredictability in each part. And the question I have is how this would extend to pipelines of models that feed on each other inputs. And one example quickly is, let's say that I have an object model, object detection model, and depending on where I see cars or faces, I trigger models that will detect faces or license plates. The latency of the end-to-end system, even though each component is predictable, may become unpredictable now, right?
So if I'm not wrong, you are referring to like these models with dependencies, so like a DAG of model executions.
Yes.
Yeah. So this is something that would
with conditional branching.
Right. So this would okay, so there are two things. One are models with conditional branching inside the models, and then just models with DAG-like semantics outside. So I think the latter can be handled on the controller by managing the right set of dependencies. I'm not yet sure how we'll tackle the first part where the models themselves have input-based conditional branching, because it slightly violates the original assumption of predictable execution. I don't know, Jonathan, do you want to add something?
All I'll add is that there are very few models that do that. That's like a very hot area in machine learning. Like you don't have models that internally have conditional branching. Yeah. The short answer is future work, I think, Rodrigo. Yeah.
Okay, great. Unfortunately, we're out of time, but this was a great discussion. I hope you enjoyed it. Thank you, Arpan, for presenting, and Jonathan for joining us. And SysRead will return next week with a talk by Zane from MIT about highly efficient, high performance farm memory, that is remote memory on other servers, swapping to remote servers. So I hope to see you back here then. And until then, have a good week. And thanks, Jonathan and Arpan again. Bye-bye.
Thanks for the invite.
Thanks for inviting. See you.